Cool title sequence. Not that I have one. Maybe I will one day. Anyway, what's up, YouTube? It's me again. I'm back with another topic review for my data science program. So if you're new to the channel, you don't know, I'm a student at a coding boot camp right now called Flatiron School. In the data science program. I'm doing the flex. It's like all online. And I just began phase 3 like a week or two ago. I'm working my way through the modules now. And my basic study strategy as I move through these modules is I try to condense everything for every module into a one-page front and back notebook paper. And the way I normally do this is I have up here topics from other modules that the current module you can't see because it's blurred out, but it connects you. I'm only in module 2, and so this will fill up later on as things progress through the module. And then this is like big ideas from the module. There's not a lot here on that side, but you can see that I filled up pretty much the whole other back of the page, which is all these are like details about the big ideas in the module. So last time I did a topic review like this, it went on for like 45 minutes, which is a lot longer than I wanted it to be. And I was doing it kind of extemporaneously the way I do my live streams, and I was just thinking that's maybe not the best way to do it for the sake of YouTube. And it would also be important to, I think, or helpful for me to learn the content, taking a different approach with these topic review videos. So this notebook paper right here is more for my reference, for me to like quickly go back and like jog my memory, like, oh, okay, yeah, I remember that. So that helps me organize my thoughts and helps me really like solidify ideas in my mind when I do that. But I decided this time to take it a step further, and I actually made a little Jupyter notebook, kind of outlining all of the big ideas and concepts in this module. So that's what this video is going to be, is me basically going through that notebook that I made where I'm sort of reviewing everything that we went through in the module. So I just want to add a little disclaimer. I don't do this on behalf of Flatiron School. I don't like know that they even know that I do this. I will, however, be using some code and example contents from the Flatiron School curriculum. So some of the code and the particular like math problems and things that you're going to see in this video are not my original work, but my commentary on it will be original nonetheless. So with that said, let's get into it. So here's our notebook here, but before we go into that, I want to show you this cool thing, and this is, I'll leave a link to this website in the video description. But this is a lot of what we're going to be talking about today, is OLS regression technique, which is, we'll talk about what that is later if you don't already know. But basically all that is the math behind how you can see when I move this data point, or really any of these data points around, it manipulates the slope of this line right here. If you kind of refer back to algebra class way back in 8th, 9th grade, or whenever you take algebra in school, you can think of this regression line right here as basically like an average of all of these like data points here. So of course, if we bring all these data points closer to the line, it might better represent like what's really going on there. And you can see how outliers might drastically like affect how well the line fits the data. So that's why, like you saw in my project live streams for the phase 2 project, dealing with outliers was a pretty big thing that we dealt with. So anyway, this is just a cool website. It really helps visualize what is going on with all this like weird math stuff that we're going to talk about today. And this is sort of demonstrating, you can see this red plane here is a regression line in 3D. So if you have like a 3-dimensional linear regression. So yeah, really cool website. I'll leave a link in the description. So after this, if you're curious about this topic, this would be just a little kind of blog post thing that I would highly recommend checking out. So now let's get into the topic review. Make sure I get all my windows and everything set up. Oh, we better start our kernel. Okay, so first let's just do like a little bit of an overview. Let me make sure I get all my stuff organized here. My outline, I mean. I'm just going to be kind of using this as like a checkbox as I go through the notebook today. So first we're going to talk a little bit about the data types pertinent to what we're talking about today. I'll actually do that right now real quick. You're going to hear me use a lot of these words right here today: scalar, vector, matrix, and tensor. And there's a visualization later on that'll make these a little bit more sense. But if you imagine a matrix as essentially like a spreadsheet or like a grid, a vector is either a row or column from that matrix, so it's a set of numbers. A matrix is a set of vectors, right? And a scalar is an individual value, so a vector is a set of scalars, right? And if you're keeping up, you'll probably infer that tensors are a set of matrices. So you can think of like a what would it be, fourth order tensor, third order tensor, I don't know. The next step up from a matrix would be basically like a 3D matrix where you have rows, columns, and like layers or planes or sheets, or there's some word for it, I forget what it is, doesn't matter. Point being that anything beyond 2 dimensions is going to be referred to as a tensor, although all of these are technically tensors of some order. So scalar is like a 0th order tensor or a first order tensor. I don't know whether it starts at 0 or 1 for tensors. But scalar is a single number, vectors a list of numbers, to put it in like Python terms. Matrix is a grid, a 2-dimensional array in terms of like NumPy. And a tensor is like a 3 or more dimensional array. We're going to talk a little bit about systems of equations, the substitution elimination method, how to solve those. That'll probably, if you paid attention in math class in school, or if you are a math person yourself, that'll be pretty familiar stuff. We'll talk a little bit about matrix algebra, basically how to solve linear or systems of equations where instead of having single numbers for our coefficients or scalars, we have like whole matrices. So that's really going to be a lot of the meat and potatoes. And then we'll get into linear regression using matrices. So which linear regression is basically like a statistically modeling technique based on linear algebra. And there's the same way you can do algebra with matrices, you can do linear regression with matrices instead of individual scalars. So let's talk first about systems of equations. So system of equations is basically right here, 2 or more linear equations that share the same set of variables. So if you have like, m plus c equals 4, and then you have like 2m plus 3c equals 6 or something like that. It's important that the 2 equations like share the same variable. So you couldn't have like m plus c equals 4 and then m plus x equals 5. That would not be exactly what we're talking about today, at least when we talk about systems of linear equations. So here's an example problem from the curriculum. Jim has more money than Bob. If Jim gave Bob $20, they would have the same amount. If Bob gave Jim $22, Jim would then have twice as much as Bob. So using systems of linear equations in algebra on that, we can essentially solve this question here. How much does each one, Jim and Bob, actually have? How much money do each of them have based on this information that we have here? So for the sake of our algebraic notation, we're going to let X be the amount of money that Jim has. So X represents Jim, or the dollars in Jim's wallet, and Y is going to be the dollars in Bob's wallet. So I don't want to show you like all of it at once. It doesn't really matter. So this first sort of factoid we have here, John has more money than Bob, therefore X is greater than Y. Doesn't tell us a whole lot. Doesn't help us like solve the system of equations necessarily, but it does. It's good to keep in mind at the end so that we verify that we got the right answer. So if we get an answer where y is greater than x, we know that we did something wrong, right? The next piece of information we have is that if Jim gives Bob $20, then they would have the same amount of money. So what that looks like in algebraic notation is if Jim X gave $20 away, so X minus 20 equals Bob Y plus 20. So Jim loses this value of 20, and Y gains this value of 20 because Jim is giving Bob $20. Right? We also know that if Bob gave Jim $22, Jim would then have twice as much as Bob. Right? So if Jim Y gave Bob $22, you see this Y minus 22. Bob's giving away $22, and Jim is gaining $22. In that instance, then this side of the equation is going to be, this side of the equation is going to be twice as much as this side of the equation. Or in other words, Bob's going to have twice as much, or Jim's going to have twice as much as Bob. So for this to equal this side of the equation, we need y minus 22 times 2, right? I hope I'm explaining that clearly. But basically, like, you take 22 away from y and you give it to x. That gives you x plus 22. But now to make sure that both sides of this equation are equal, we know that this is twice as much as whatever Bob has. So we wrap it in the parentheses and put a 2 around it. We multiply it by 2. So now using the elimination method, which is essentially where you eliminate like variables or any sort of like digits that you can get rid of easily, that sort of thing. Doing a little bit of simple algebra using elimination, we can find that x equals y plus 40. So we take equation A, basically, and we add $20 to both sides. So that's going to cancel out the 20 here, and then we're just left with x over here. And that 20 we're adding over here turns this into 40, so that's how we get x equals y plus 40. And we're going to call that equation C, just to kind of keep everything organized in our mind, right? Now we can use substitution. So now we've solved for one variable, we can substitute the equation representing that variable in a different equation, right? So now that we have something that represents x that isn't x itself, we're going to plug that into equation B. This x plus 22 equals 2 y minus 22. So you see here we just replaced x with y plus 40, right? Because we know that x equals y plus 40, so we can just replace it there. Now we do a little bit of simple algebra. When you're doing substitution, anytime you're doing like algebra like this, where you're balancing equations, generally my intuition is to follow PEMDAS. So even though you're on two different sides of the equatorial or whatever this is called, so like if we immediately added, like, say we know that y plus 40 plus 22, that's 62, that could potentially get us into some trouble. So you want to, generally you have the best luck, I find, if you follow PEMDAS when you're balancing equations like this and doing substitution, that sort of thing. So the first thing we're going to do is divide both sides by 2, because we're multiplying by 2 here. So to get rid of this, we're going to divide both sides by 2. So we're left with simply y equals 22 over here. And we then divide 22 by 2, 40 by 2, that gives us 11, and 20, and then y over 2. Now we can easily add 20 and 11 to give us 53. I see what I did here. So we can add 20 and 11, that gives us 31, but then we're also going to add 22 to both sides. That's going to cancel out this 22 here, and we're going to add 22 to that 31, and that's going to give us 53. Sorry, I was trying to be not extremely verbose when I was writing this. So that's what's happening here. We're adding everything up here, and then we're adding 22 to both sides to get rid of this, and that leaves us with simply y equals y over 2 plus 53. Now, we want to multiply both sides by 2 to get rid of this 2 right here, and that's going to leave us with 53 times 2 is 106. Multiplying this by 2 is going to cancel it out entirely. Remember, you can basically imagine a 1 next to this y. So if we multiply that by 2, then that's just going to it's going to cancel it out, and we're left with y equals 53 times 2, which is 106. So now we've solved directly for y, directly to a scalar and not some variable. So now we can substitute again y into our equation c that we got here. So then we know that x, replace the y with 106, x equals 106 plus 40, x equals 146. So we know that Bob has $106 and Jim has $146 based on this information that we were given here. And that's basically systems of equations. As long as you have the same set of variables, then you can pretty much solve for any variable. And you also, of course, like need some constants in there too. If it was just like x plus y equals y, then you wouldn't be able to do anything. Or like this right here, there's no constants here. So like I said, that doesn't help us solve the equation, but it does now help us ensure that we got the right answer, and we know that 146 is of course greater than 106, so x is indeed greater than y. So that's systems of equations in a nutshell, or a quick example of it. Again, here's a good visualization of exactly what I was talking about earlier. I was talking about scalars, vectors, matrices, and tensors. Cool picture. I don't have much else to say about that, honestly. But in the same way that you can solve systems of equations where, so like we know that this x and this y, anywhere it occurs, what it's basically representing is some unknown scalar value, right? A single number. However, we can also do algebra in that same way with vectors and matrices, where those variables, those letters that you see, represent sets of numbers in the form of either vector or a matrix or a tensor as well. That's a little outside the scope of today. Mostly we're going to be dealing with vectors and matrices, but point being that you can do algebra with any order of tensor as well, as long as you have, again, the same set of variables. So let's talk a little bit about the different types of operations that you can do on matrices, because it's not exactly, the math doesn't exactly work the way you might intuit it to. Let me toggle breadcrumbs. No, I'm not going to worry about that now. I kind of want to make this collapse, this toolbar here, but it's okay. So anyway, your intuition might be, if you have two matrices, to just like multiply the numbers by their corresponding index, right? So if you have like a matrix of 4 values, like 1, 2, 3, 4, you might multiply one, and another one, the matrix of like dimensions, you might multiply like 0, 0 by the 0, 0, like that coordinate. That only works when you have two matrices of the exact same dimensions. It's also, for reasons that I'm not necessarily aware of, not used that often. It's not extremely useful for actual data analysis and that sort of thing. But anyway, that's called the Hadamard product. And it's notated with this little circle symbol here. So every time you see that, you just know that that's the Hadamard product. And you can do this in Python by simply typing, declaring like some matrix to a variable and multiplying it using just the multiplication symbol on another matrix that's assigned to another variable. There's also a thing called a cross product, which if you just Google cross product, you can see some like good visualizations on this. but it results in a vector that's perpendicular to each of the vectors being multiplied. So this only works with vectors, is kind of like the big takeaway here. You can imagine a vector is a set of numbers. So if you imagine like a 3D space, right, that might be like points along a line. And if you have two sets of points along a line, two vectors, your cross product is when you multiply those vectors by each other, it's going to end up giving you a vector that's perpendicular to the two of them, right? So you'll have like two vectors going like this, and then another, your C, your resulting vector, when you multiply it, will be perpendicular to the two of them wherever they intersect at. Kind of interesting math going on. Not very useful, at least within the scope of what we're talking about today. I'm sure it's useful within the scope of math, but in the scope of the data science necessarily, it's not exactly going to be used a whole lot. You do have you can do this pretty easy with code. You just use your NumPy library and use a dot cross method, pass in your vectors, and you're good to go. Dot product is what we're actually going to be using a lot today. So it's most commonly used, at least for linear regressions or solving systems of linear equations with matrices, matrix algebra in other words. There is one big caveat here, you see like in big bold. So you have an array A and array B. And array A must have the same number of columns as array B has rows. Okay, and this is your calculus notation for it. If you don't know this sigma symbol in calculus notation, at least, basically I think of it as it represents a for loop. But you can see that A, I, K, and then B, K, J. So you have a K and a K here. That's representing the fact that A has the same amount of columns as B has rows. So in this notation, it's like rows, columns always. So also an interesting thing to note is that the resulting matrix is going to have the rows from A and the columns, the amount of rows from A and the amount of columns from B. Again, this can easily be achieved in Python using NumPy, using this dot method right here. Transposition is an interesting thing to understand. Transposition is used quite a lot throughout this module. The big thing that it took me, I had to it's not complicated, but I had to stop and think about it for a second. You rotate your array 90 degrees, but then you also have to reverse the order of each row in the array after you've done that. So you can see this array here, if we were to only rotate it 90 degrees, you would have 1, 2, and 3 right here where 7, 8, and 9 are, but it's over here. So you have to rotate it 90 degrees and then reverse the order of each row. So those are different types of operations that you can do on a matrix. Mostly we're worried about the dot product and the transposition. And yeah, we're going to talk about inverse matrix next. So there are some special matrices. I don't know why this is. Yeah, there we go. So there's the identity matrix. Before we talk about inverse matrix, there's the identity matrix. And basically the identity matrix is the matrix equivalent of the number 1. We'll talk about a little bit more in a moment, but basically you'll know from arithmetic that any number multiplied by 1 is simply, or 1 multiplied by any number n is simply going to be 1. Or that should be an n there. Anyway, 1's a really cool number, or really interesting, does a lot of good things for math. I'm getting a little bit out of my depth here with all this math stuff, but that's what these videos are for. So anyway, the identity matrix is a square matrix in which all scalars along the major diagonal, which is just the top left to the bottom right, are 1s, and everything else is 0s. And when you actually, in the real world, find the identity matrix of a given matrix, you will sometimes end up with really, really, really tiny decimals, and you just round, and that pretty much solves that problem. But basically, any like dimension of a matrix has square matrices at least has an identity matrix associated with it. But you can see here, this is a great example. You have just 1, 2, 3, 4, pretty simple matrix, and this would be the corresponding identity matrix. It's available in NumPy using the dot identity method, where you pass some array into it. And this is your sort of mathematical notation for it. And so this is what I really mean by it's like the matrix equivalent of 1. Because, yeah, this should be in. So yeah, any matrix times its identity matrix is simply itself, right? And that's what makes it similar to 1. You can't have, by nature of being a matrix, you can't have just multiply a matrix by 1 necessarily, so you have to have this thing called the identity matrix. And that's basically what it serves as, is 1 in the world of matrices. Just like you have inverse numbers elsewhere in other like fields of math, you have the inverse matrix in matrix algebra. And we won't get into the math of how the each individual scalar is calculated, but the big takeaway here is that a matrix times its inverse is its corresponding identity matrix, right? So that is really useful because there's no definition for how to divide matrices, right? So we use the identity matrix, or the inverse matrix, to compensate for that fact. So there's a little example here from the curriculum. So you imagine you have 10 apples you want to share with 2 people, and you can divide it by 2, which is what most like normal people would probably do. Or you can also multiply by 2's reciprocal, or the inverse of 2, which is 0.5, and that gives you the same answer. So although there's no defined way to divide matrices in matrix algebra, we can achieve what would be the same result by multiplying by the inverse matrix. So that's what's really cool about the inverse matrix. It essentially allows us to do division on matrices without like actually doing division. So, oh my god. There we go. It keeps like these texts keep like showing up behind the markdown, and when I rerun the cell, it just like fixes it. So we're just gonna deal with that, I guess. But anyway, so for a single linear equation, you can basically do algebra on it if you respect the principles of like the dot product and transpose properly, and respect the principles of your identity matrix and all this other stuff that we discussed above. With respect to those rules, if you will, you can solve systems of linear equations and do algebra on matrices. Do algebra where your coefficients represent matrices. Right. Little notation note, you'll notice that these are all big capital letters now. So anytime you're dealing with anything beyond simply a scalar, when you have like a set of numbers, you're going to have a capital letter representing that. So I kind of want to get into like really like the code stuff, but this is basically a proof for how you would solve for x from here, right? So we multiply both sides by the inverse, and then we know that multiplying anything by its inverse is simply that own thing, so we can cancel out like this here and just replace it for I. So now we know that the identity matrix of A times x equals A inverse times B. And again, with substitution, we can eliminate I, because we know that anything multiplied by the identity matrix is itself. We know that x is going to have the same dimension. The identity matrix of A is going to have to be the same identity matrix of x, because you're going to have the same dimensions, right? So we know that x equals inverse of A times B. And we already knew what A and B were in the first place, so assuming we had those matrices in front of us, we could easily do that calculation, right? We could have done this above with that the systems equation we solved earlier, but you can basically create a matrix from a system with linear equations. If you have more equations, you could just like add rows or columns or whatever's necessary to your matrices to do that. But this is what that would look like if you were going to notate in matrix notation a systems of equations. Sorry for moving through this a little fast. I feel like most of what this is about is like the actual like data science and writing the code and whatnot. So I don't want to dwell too much on like 8th grade math stuff. But so here's a example problem, and we're gonna solve it with Python now. So a coffee shop is having a sale of coffee and tea. On day 1, they sell 29 bags of coffee and 41 bags of tea, and they sold that for a total of $490. So we notate that as 29C for coffee and 41T for tea equals $490. And likewise, they sold 23 bags of coffee on day 2 and 41 bags of tea on day 2 for a total of $448. So how much does each bag cost? So first we're going to import NumPy. Then we're going to define our matrices. So this is basically a Python-y version of this type of notation right here, right? So this first matrix is my matrix A. So these are my coefficients, 29, 41, 23, 41. You see here. It's written a little weird, but imagine this is what you're looking at. Now that looks a little bit more like matrix notation, right? But it's kind of ugly code to read. And then, of course, we have our constants, I guess you would call them. The $490 from day 1, $448 from day 2. And each one of these sets of brackets is a row. We have a 2x2 matrix here so that we know that we're kind of satisfying that columns and rows thing. So that means that we can in fact find the dot product of these two matrices, and we can do math with them together. But first thing we're going to do is find the inverse of matrix A. And we're going to transpose T or B using this .t method here, and that's just positioning matrix B in a way that it's compatible to run your dot product with. And then we have our inverse of A, we have B transpose, we can find the dot product of both of those. And remember, because we know from above that X equals the inverse of A times B, so we're setting our variable X to equal A inverse, which we've defined here, dot product with B, which we've defined here, and we just transpose it here to make it compatible for the dot product. We're going to run that, and we find that a bag of coffee and a bag of tea are both $7. So that's how you would solve a system of equations for matrix algebra with Python. All of that is really just like to drive home a point. I wouldn't recommend actually coding it in that way, especially with larger and larger data sets. So this can all be done pretty sleekly in a couple lines of code right here. I don't know what that was. But you see that gives us the same answer. So this is a pretty just sleek NumPy method that we have available. So let's get into the real meat and potatoes, the regression analysis. Man, I don't. It keeps saying. You see what I mean? Like it says cells hidden, and it's like there's no cells hidden. Could be in a punk. Anyway, so regression analysis is basically when you fit a mathematical model, which is represented by this line here, to observed data points. The resulting line, the regression line, represents what the model's predictions are based on the model. So if you imagine this line kept going on, the model's predicting that any new data points are going to occur along that line. Of course, we know that it's not going to perfectly fit that line as we go, and that gets into like our error terms and stuff, which we'll talk about in a minute. But that's basically the idea. You've probably seen this equation before, y equals mx plus c, or b, as it was taught to me in school. But basically, c is the y-intercept when mx is equal to 0, right? Or in other words, it's at any given point on the x-axis, the distance between the x-axis itself and the regression line, if you wanted to think about it like that. And mx is more or less the slope of your line, your rise over run, if you remember that from school back in the day. Also, I'm going to link this notebook in the video description if you would like to read this notebook more in depth later on, because I don't want to just like read all this like verbatim, right? I don't even know how long. We're at 36 minutes now. Okay. So, what time is it anyway? It doesn't matter. We're gonna finish the video. So, that's a broad overview of what model fitting is. Is you're just doing a bunch of math stuff to try to get this line to fit this cluster of data points as closely as possible. So for instances where you're using only vectors, you can use this polyfit function in NumPy. But like I said, the big limitation here is that only works when you're dealing with vector inputs, so like not necessarily matrices and that sort of thing, which might be useful for like some use cases. But you can see here we have some random data generated, and we have this line where the data is completely random, so of course there's not like a real relationship to be found here. But you can see how this line is like trying to find like it's basically trying to draw a line where the cumulative distance from between all these data points to the line, so from here to here, from here to here, from here to here, and from here to here, if you added up all those distances, those are called your residuals. It's trying to find the line where those residuals are the least. So that works a lot better when the data's not random. But just to kind of show you an example of the code, right? Pretty simple stuff as far as the programming side of things goes. So when we're dealing with how do I put this? When we're dealing with matrices, and especially when we're trying to like minimize our error term E, this residual thing I'm talking about, we do that using a method called ordinary least squares, which is a type of regression modeling. As I understand it, there's other forms of regression modeling. Ordinary least squares is just one of them. So I'm trying to like not read this verbatim for you. Basically, we end up with doing a little bit of like algebra and proofing. We end up with this formula where beta b equals x transpose times x, the inverse of that, times x transpose y. we're assuming that we already know the values of x, which is a matrix, and y, which is a scalar value, I believe, or it might be it's a vector, because it's an intercept. So you can imagine that can be solved with some algebra, like relatively easily. So with least squares regression, what we're trying to do is solve for the expected value of weights, which is referred to or notated as x hat, which you need to solve this above equation. You need to solve for beta in order to calculate x hat. So that's what we're about to do. So like I said earlier, the goal is to choose the vector x for unknown variables to make e, our error term, as small as possible, right? So we're trying to, visually speaking, we're trying to make the gaps between these data points in this line cumulatively as little as possible. Whew. Okay. So the first thing we want to do is we're first going to import the data, and we also need to, when we're doing matrix algebra, or when we're doing ordinary least squares, we need to add a column to our input matrix to represent the intercept, or refer to the intercept rather. And that's simply, we're going to add a column of ones in the first index position as the first column for our input matrix. Sorry. So we're going to import a little bit of data here. This is just like some real estate data from the curriculum. And so right here, you can see that we're adding a 1 at the beginning of each row. And then we're appending that row to this list that we instantiated. So this is going to end up being a list of lists, an array, in other words. And then we're actually making it an actual NumPy object into an array right here. So all this should give us a nice little bit of data to work with. I don't know why that was there. But anyway, we know that this is basically the same formula that we saw above, just notated a little bit differently. But yeah, the point being with the ones, adding the column once at the beginning, if you don't do that, then the function, the regression line, will be constrained to the origin, meaning it will always go down to like the bottom left corner and then like up and away somewhere, but it'll always start at that bottom left corner. And you can imagine that's going to limit its predictive abilities with the data. It's going to limit its ability to fit the data, right? So now that we have our data sort of prepared, and again, we're also assuming that this is all like numerical types, and there's no missing values, and like all the same stuff you want to go through when you're preparing data for analysis. So now we're going to randomly sample the data into a set of training, or a sample of training data to train the model with, and then a sample of test data to test the model with and help us make predictions. 80-20 is typically used. There's no like rule or law that you can't do like 95-5 or 90-10 or 60-40 or whatever. But 80-20 is pretty typical, pretty standard, at least in the data science world. So we can do that in Python pretty easily. So we take our array of indices. So this is basically like the index position of every row in our array. So we're like sampling rows of data, right? Because it wouldn't make sense to sample columns because those are completely different features. You can think of every row as a vector itself, as a data point. So we use the random module from NumPy, and we use this choice method to randomly sample from our data, and we're getting this, that's why we're using this like 0.8 number right here, is because we're trying to get 80% of the data, and we want to only use, we don't want to replace the data that we're sampling. We're going to, like, whatever we don't take for our training sample, we want to leave for our test sample, and we don't want to put back anything that we do take for our training sample. So we set replace to false here. So we get our sample of training data, we get our sample of test data. This little squiggle here for NumPy is basically like means the complement. So this is saying everything in the indices that is in the training IDX, we want the opposite of that, the complement. So that's kind of what's going on here. And we're going to subset the data. So now that we have our, basically like what train IDX and test IDX is a list of indices of the rows that are chosen for our train and our test samples. Now we need to actually grab those samples themselves, and we're going to do that by index slicing. So that's what's going on here. And we declare these variables. So now we basically have two different arrays, train and test, to represent that data that we've sampled. And it's important to note that somewhere up around here, I set a seed, just because mainly because I wanted to make sure that this visualization was the same time every time I recorded this. So this isn't exactly like genuinely random in this notebook, but if you don't set your seed, this will be genuinely random, or at least random as far as NumPy goes. There's some limitations to that. Like if maybe I shouldn't say genuinely random, but it'll be random enough for your purposes of data analysis at least. So we're just going to make sure we got the correct shapes. So our original data had 546 rows and 13 columns. We see that we didn't lose any columns here, so that's good. And we know 437 plus 109 is indeed 546. So our train test split looks good. So now we need to remember in these variables here, train and test, that's everything. It's our set of input vectors or features, like big X, if you will, and it's also the feature that we're trying to predict, Y. So we need to sort of separate those two. So that's what we're doing here. We have X train and Y train. We're essentially grabbing like the particular column that we're trying to predict and everything else. It's not that. We're grabbing that from our training data, and we're doing the same thing here from our test data. So now we have X train and X test, which are matrices, so to speak, or arrays, however you want. NumPy, it's an array. Math, it's a matrix. NumPy also has matrices too. Same thing. Anyway, we have our X train or X test, which are matrices or arrays of data, and then we have our Y train and our Y test, which are both vectors of data, and they've both been randomly sampled from the same population of data. So we have that here, and again, if you just kind of want to check and make sure that we have everything's like copacetic. So you see now that we only have 12 columns in each one because we've removed a column, our Y column, and we do still in fact have the correct number of rows in our predictors as well as our estimators, or like our big X. Okay, so recall this formula from where'd it go? Here. No, that's not what I was thinking of. This formula right here. B equals the inverse of X transpose times X times X transpose times Y. So to put that in sort of NumPy notation, that is this right here. So the x transpose of x train times x train itself, the inverse of that, times the transpose of x train times y train. So we're using all of our training data here to calculate beta, or our beta vector. So the biggest problem, the challenge for me a lot of times is reading this calculus notation type stuff and then like transcribing it into code, right? So this whole block of code right here is basically what's going on in this parentheses right here. And this whole block of code right here is basically what's going on the right side of the dot product or dot operator right here. And this is essentially the whole equation once all of these little bits are defined, right? So we get, we declare xt, and that's just the transpose of x train, right? And then we declare xtx, which is x transpose times x train. And again, we're using the dot product for that. And then we have the inverse of xtx. So that's this whole deal right here. So this line of code basically represents this whole, and everything on the left side of the dot operator right there. So that's what's going on there. And then this xty is everything on the right side of the dot operator, right? So we have x transpose and y train. It's worth mentioning too, you can also notate this in NumPy as xt dot y train, if that's easier for you to read. But yeah, so everything left side of the dot operator, everything right side of the dot operator. So now we have basically xtx inverted and xty. This alone is basically the whole left side of the dot operator, and this alone is basically the whole side, the whole right side of the dot operator. And here you can see I use that kind of slightly different notation. I don't know why. It doesn't really matter or make a difference. But we have xtx, the inverse of xtx, dot product of xty. That's all that is here. We're going to call that beta. We're going to run it, and boom, we have our beta matrix. Zeus is back there moaning and groaning because he's bored. Math was once upon a time boring for me too. Now I'm like kind of slowly evolving into a huge nerd about it. So now we can use our beta vector to make predictions. So we basically take the dot product. We go through every row in our testing sample, and we get the dot product of that row with the corresponding row in our beta matrix. So that's what this is. For every row in x test, now we're with x test, we make our prediction using row. So that's all 12 data points in that vector, that horizontal vector, and we multiply it by beta, because we know that row is going to have the same columns as rows are in beta. So we can take the dot product of it. So then we append that to our list that we've instantiated here, and we print it, and now we have a matrix of predictions for y. And we could do a lot of things with this. We could plot it. We could do all sorts of stuff. This, in mathematical terms, is going to be referred to as y hat. So moving on. Now that's basically we've built our model at this point, right? So now we're going to evaluate like how good of a model is it, like how reliable is it to use. So the first thing that we're going to do is plot our observed data points against our predicted data points. And we get this visualization here. And it, upon visual inspection, it doesn't look that bad. We can see that there's like some outliers here, and there's maybe even like a trend or cluster of outliers that we could maybe like fit a little bit better. But generally speaking, like we're pretty point on point here. But that's great to look at and kind of gives you a hint at if you're moving in the right direction or anything, but it's not quantitative, to say the least. So to quantify exactly how accurate our model is, we want to look at what's called the root mean squared error, which you can basically think of it as an average for how much error there is in your model. So we have all these residuals here, which is like the distance. Again, why am I? There's like a highlight thing under my cursor. Anyway. Huh. Okay. So we have all our residuals here, which is basically like the difference between our observed data points and our actual data points. So you can think of your root mean squared error as a mathematical representation of that for the whole model, or an average of your residuals, basically. It's not exactly that. It's not that in mathematical terms, but if you want to like think about or conceptualize it in that way, that's might be a good way to think of it as like there's different types of averages, and that's like a sort of average for it. But don't you think about it that way when you're taking like a math test. So anyway, it's our root mean squared error is defined in our calculus notation as this right here. Again, this sigma symbol is basically a for loop is what that means. So again, we're going to take this formula and we're going to turn it into code, right? So we're instantiating an empty list here just so we can have somewhere to put our data when we figure it out. This is this little bit of our formula right here. And again, so we're this sigma n I equals one thing. All that's telling us is that we're iterating over however many rows there are in like our input matrix, basically, right? So, and then the I represents, so you can think of I as like changing as you go through n. So starting at I equals 1, you're going to go to like 2, 3, 4, 5, 6, so on. So for every index, basically, on axis 0, right? For every row in our matrix, we want to take our predicted data point minus our actual data point, and we're going to square that, and that's our squared error, right? It doesn't get much simpler than that. It's like the error squared. So we're going to append that to that empty list that we got there, and so then this will give us a essentially a vector of our squared errors for all of our data points. And then you see this, all of that is over n here. N is the number of data points in our input here, right? So that when you take something, any kind of like sum or whatever, and you divide it by the number of data points in that thing, that's an average, that's your mean, right? So that's all that's saying here is you wanted to get the mean of this collection, this collection of data. I keep thinking I have like a marker that I can like draw with, but I don't. So we take our mean squared, to get our mean squared error, we just take the mean of our set or vector of squared errors, right? And then of course, to get our root mean squared error, we take the square root of our mean squared errors. We can run that, and that gives us this really big fat number here. As it turns out, that is in terms of our target variable, y, which in this case is house prices. So that doesn't seem like as ridiculous of a number when you're thinking about house prices, going into the hundreds of thousands and potentially millions. Having being off by $15,000 is when you're talking about 250,000, $500,000, $1 million houses is like really not that much. However, we want like to think about that in a little bit more objective way, because that's not exactly the right way to think about it. That's not telling us that our any given data point might be off by $15,000. This is in terms of our predictor or target variable, right? And we have a lot of different variables in this data set. So we didn't go into it in depth, but you can imagine it's a real estate data set. So there's things like probably like the square footage of the house, the number of bathrooms, the size of the lot itself, all that sort of stuff, which is not, a lot of that's not even in dollars, right? So we want to normalize that. So like how off are we for any given feature? You know what I mean? Not just specifically for the target feature or the target variable. So to do that, we find the normalized root mean squared error, which is defined by this formula right here, which is not that complex, frankly. So we take our root mean squared error, which we've already calculated, and then we're going to get the difference between the maximum of our training sample, our training target sample, and the minimum of our training target sample, and we're going to divide the root mean squared error by that, and that gives us our normalized root mean squared error, which is when I wrote this notebook last time it was 0.08, now it's 0.09, because I thought I set the random seed. I'm gonna go back and look at that. That's interesting that it actually gave me a different result despite setting a seed. But nonetheless, generally, like you want things like in a range of like 0.2 to 0.5, and this is well below that. So this is indicative that it's a pretty strong model, and we can qualitatively analyze it and make some good decisions based off of what we find in this model. So all that math, as I go through this module, was really fascinating and really interesting, and I started to like feel like I understood it and I was getting a grip on it and I can like do stuff with it, and come to find out that that's really not the way you would actually want to do stuff in the real world anyway, because of this thing called computational complexity. So basically different algorithms have different run times, and they're described in terms of this thing called Big O notation. It's a really cool visualization from the Flatiron curriculum. And so basically, like, the x-axis here is as like the data sets get bigger and bigger and bigger, this is how much more time an algorithm would take to run. And this isn't in terms of like minutes or seconds necessarily, because you can imagine like it's kind of like relative to the machine that it's running on, so to speak. So if you imagine there was just like a super powered like Turing machine, there would still be like some difference in how efficiently it could run like one algorithm as opposed to the other, if you know anything about Turing machines. And as it turns out, according to this proof here, oh, whoops. Now it's pretty. As it turns out, the OLS, ordinary least squares regression, is very expensive in terms of computational requirements. So if you follow this little proof here, you'll find that basically we do a lot of like transpositions and inversions when we're doing OLS, and it comes out to a big O notation of k squared times n plus k, n being the amount of rows and k being the amount of columns that you have, which is extremely expensive. So it basically comes down to you can't do OLS with big data. Anything with less than 1,000 columns and less than 1,000,000 rows, you can probably get away with it. But any like data set that you're dealing with that's bigger than that, you're going to be sitting at your computer staring at the screen waiting for a really long time for that algorithm to actually run. So you can imagine the debugging process would take ages if you had to wait for the whole thing to run just to see like what went wrong. So it's really great to understand all that math and algebra and stuff, but unfortunately in big data at least, ordinary least squares is not the preferred method to perform regression analysis with. And we're going to learn about how to deal with that in the next modules, I believe. So the big point being the linear algebra stuff was like really cool. And the thing about like using like the inverse matrix to get the same result of what would be the result of dividing a matrix, but you can't really divide a matrix, like that whole thing was just like super interesting to me, for one. Also, I'm losing my train of thought. I'm trying to wrap this up too. OLS is really powerful. You know, like if with with the right size data set, it's like a really solid like strategy to use. It's very, the formula, the actual like math itself is pretty like sleek and pretty intuitive. And so it's unfortunate that it's so computationally expensive, because it is such an elegant formula. But there are some use cases for it, but it's just like in the modder. I'm so sorry for these typos. I was up till like 3:30 last night putting this together, so sorry about that. In the real world context, there's more and more data every day, and so like, you know, even like regular data is becoming big data. So unfortunately, there's not especially at least in the field of data science, there's not a whole lot of use cases for OLS, ordinary least squares. But understanding like the algebra and the math behind it and how it all works can give you insight into how other sorts of algorithms work, and you know, how to debug them and manipulate them, and like utilize them to your advantage and that sort of thing. So if you're getting into data science, I would highly recommend getting into the math of ordinary least squares, if nothing else, just to give you some context and some deeper understanding of like what's really going on with your other algorithms and things that you use, and it'll probably, I would imagine, improve your ability to utilize other algorithms as well. So with that said, that is the module 22 topic review on linear algebra. I hope you enjoyed it. I hope you hung in there, at least like skipping through like the important bits and the bits that you did enjoy and whatnot. This video is now officially a little bit over an hour, so I hope you got some value out of this. I hope you learned something, or if nothing else, if you're considering going to a boot camp, you're considering going to Flatiron, and you're really like serious about doing data science, I hope this gives you an idea of what Flatiron really has to offer, because like I said, it falls in the category of coding boot camp, but you can see most of this module, at least like the last week I've been doing like a little bit of code, but it's been a lot of like mathematics and theory and stuff too. So we're doing a lot more than just coding. We're genuinely like learning data science. So if you're trying to pick a boot camp to go to, and you're decided on data science, if you're on the fence about software engineering and data science, I can't really speak to that. But if you're decided on data science and you're trying to pick a boot camp, I think Flatiron's a really great one to go to, because you're going to learn a lot more than just how to write the code. You're going to learn like deeply what you're writing code about, and I think that's incredibly valuable in terms of being valuable in the job market. All right. So next module is a little bit of calculus and this thing called gradient descent, which is going to address some of that big O notation, like computational complexity issues I talked about a second ago. So that'll be really interesting. Again, I'm going to do another topic review. It's going to be the same thing. I'm going to have my one pager, and I'm going to make a Jupyter notebook based off my one pager, and we'll do a little video about it, or a long video about it, I guess. I did just cram 50, 60 hours of coursework into 1 hour, so I guess that's not too bad, all things considered. So anyway, like I said before, I hope you enjoyed it. Share this with your friends. Check out the links in the description below, and I'll see you next time.